welcome to this video on Voxel Space rendering. So recently I came across this awesome algorithm called Voxel Space, which is used to render terrains like this, and it's a pseudo 2.5D method of rendering, and I wanted to implement my own version of Voxel Space engine using a game library called Raylib, which is implemented in C. Now, what's so special about Voxel Space engine? As I already mentioned in the beginning, Voxel Space is used to render terrain graphics like this. It was developed by Novalogic developer Kyle Freeman in the year 1996, I believe. So it was created way before the advent of any sophisticated 3D rendering engine, graphics acceleration or hardware acceleration. It does the entire rendering pixel by pixel on the screen without any sophisticated 3D graphics algorithm. Let's see what kind of terrain it generates. So here's my implementation of Voxel Space in C. Let's have a look. So I've added a few basic keyboard movements, like I can move forward, move backward, rotate my camera, move the camera up and down, tilt, right? The terrain implemented or the terrain generated by Voxel Space is quite good, despite the fact that no 3D polygons are being used. It's pretty decent, right? And as I said, it's from 1996, and one of the first games that was created using this, like one of the first game that Novalogic created using this algorithm was Comanche, right? So yeah, this was the first game called Comanche that was implemented using Voxel Space algorithm, and since then the algorithm has been developed and it has become way more sophisticated than what it was when Kyle Freeman wrote it. Coming back to the implementation, let's first understand how Voxel Space works. So in theory it's very similar to how raycasting works, right? Raycasting is one of the very first pseudo 3D algorithms. So again, Voxel Space is also a pseudo 3D algorithm, or rather it's a 2.5D, and because it's not pure 3D that we are seeing, it's more of a pseudo 3D that we are seeing. How it works is pretty elegant. As I mentioned, it's pretty similar to raycasting, but unlike raycasting, there is a concept of height map and color map in Voxel Space. So what is a height map and what is a color map? A color map looks something like this, right? The color map will tell us how each pixel on the screen will be colored, right? So this is our map. This is how our map will look like, and we can find the color information of every pixel from this map, right? Once we know which pixel we want to render, we will look up this map to find which color that pixel is going to be. And next we come to height map. The height map is pretty much a black and white map. Each pixel is just 8 bits because it's a value from 0 to 255. The value from 0 to 255 determines the height of the pixel on the screen, right? So this will give us with the position where the pixel will be drawn in every column of the screen, and the color map will give us what color that pixel will be on the screen when rendered. Both these maps are 1024 pixels by 1024 pixels, both the color map and the height map. Now let's find out how Voxel Space works. So let's say this is our map. This is our entire map of terrain. This is not a screen. This is not what we are seeing, but the actual map on ground, right? So the first thing for Voxel is a camera. We need a camera. Camera is pretty much what the player is gonna see. So the camera will be our eyes. So let's say our camera is located somewhere over here. So this dot is our camera. And next what we need is a field of view. So a field of view is an angle, and everything that falls within that angle is what we are able to see. Let's fix our field of view. This is the left extreme line of our field of view, and this is the right extreme line. Now what we are free to decide is what should be the value of this angle, what should be the value of this field of view, right? One very good value for this angle is 90 degree. because it gives us quite a few advantages when we do our mathematical computations. Like when we calculate the various parameters of voxel space, the choosing this angle as 90 degree will give us a lot of advantages. So let's assume this is 90 degree, right? Also, let's assume we are looking up. This is where we are looking. So on this map or on this terrain, we are our player or our camera is right now here, and we are looking in this direction, right? And this is our field of view. Like this entire angle is our field of view, right? Now what we are going to do is, let's say this point is x comma y, right? This point is x comma y. If this is x comma y, and let's say how far can we, or we need to decide further how far can we look into our z direction, like how far can we look into the z along the z axis. So this is our z axis, and how far can we look into the terrain along the z axis. Let's call it z far. Now if I join these two lines, you will see, since this entire angle is 90 degree and this I am looking straight, and my line of sight is such that it is exactly bisecting the field of view. So this portion is half of field of view and this portion is half of field of view. If my field of view is 90 degree, so this becomes 45 degree, and since this is also a 90 degree, this also becomes 45 degree, and hence this becomes a z far as well, right? And if we know this is z far and this also is z far, we can easily calculate this coordinate and the coordinate of this point, right? So this will be x minus z far comma y. Sorry, this will be x minus z far comma y plus z far, something like this, and this will be x plus z far comma y plus z far. Again, this is a special case. I chose this special case because it's easy to explain with this special case when the player is looking exactly upwards without any rotation of the player. This of course will change as and when the player rotates the camera, and when that happens we will have to use some trigonometry to know what is this, in which direction the player is looking, and accordingly we need to decide what will be the coordinate of this point and this point, right? But as of now, let's use this to understand how voxel is working. Let's say this field of view is what that will be rendered on a screen. Doesn't matter what is the distance between this point and this point. This entire distance will be the width of our actual graphics that will get rendered on our screen, on our actual computer screen. What we are going to do is, the original resolution of Voxel Space when it was created was, the screen resolution of Voxel Space was 320 pixel width by 200 pixel height, right? So let's consider that our screen will also be 320 by 200, although in my implementation I've considered screen width to be 640 and screen height to be 400, just the double. So I've scaled it by a factor of 2, just made it double. But in this case, let's consider that our screen width, let's say this is our actual screen where we are seeing the terrain being rendered. This is 320, this width is 320, and this height is 200. What we are going to do is, we are going to divide this distance from x minus z far comma y plus z far to x plus z far comma y plus z far into 320 columns, right? 320 columns. So like 1 column, 2 column, 3 column, like this. There will be 320 columns. For every 320 columns, we are going to cast one ray from x comma y to the extent to which zfar goes, right? So for every column of those 320 columns, we are going to cast a ray from our camera, and for each and every ray, for let's say this is one such ray that has been casted. Let's say this is one such ray, this is another such ray. For each and every ray along that ray, for every pixel, we are going to calculate the offset of that pixel. Let's say this is one pixel, this is another pixel, this is another pixel, this is another pixel. For every such pixel, we are going to calculate the offset of that pixel on this map, right? And using that offset, we are going to look up our color map and height map, and we are going to find out the color of the pixel and the height of the pixel. In order to calculate the offset, we'll employ some trigonometry, which can be found in the code, right? This is how we are somewhere over here. This is how we are calculating the offset. First, we need to find out the delta x, the delta y. So what is delta x and delta y? We run a loop from 0 to zfar, and for every unit progress along zfar, we calculate the delta along y-axis that we are going and the delta along x-axis that we are going, right? And like that, we calculate dx and dy. And to calculate the position of the pixel, we simply keep adding dx and dy to x and y. And once we have the pixel coordinate on the map, we calculate the pixel offset on the color map and height map using this formula here, right? So since this is two dimension, but when we fetch the pixels from the color map and height map, it will give us a single array of pixels, right? So we need to translate our 2D coordinate of the pixel into an offset in the pixels array that we get from the color map and the height map. And that's how we get the offset of the pixel. Now comes the rendering. How do we show the pixel actually on screen? In my implementation, I've employed something called front to back rendering. So I've painted the pixel front to back. The reverse can also be done. We can start painting the pixel back to front, but you'll see that we get some advantage when we print the pixels front to back. So let's say this is my screen, and on this screen, let's see the lateral view of the terrain. Like let's say I'm viewing the terrain from a side, right? So let's say one pixel is over here, right? One pixel is at this height. This is one pixel. The second pixel I'm drawing over here. Let's say the second pixel's height on screen is less than that of this first pixel, somewhere over here, right? In this case, if you see, let us consider my eyes. This is my eye, and this is the z-axis, right? This is the z-axis. This is my screen, right? So I'm viewing the screen from the side, right? And let's say this is my entire monitor screen, and this is my eyes, and this is the y-axis, this is the z-axis, and this is where the pixels are being painted, right? And let's say one pixel is of this height and another pixel is of this height, and this pixel is behind the first pixel. So do we need to render this pixel? No, we can avoid it because this pixel will be hidden by this pixel, right? Let's say there is another pixel which is drawn, which needs to be drawn at this height, right? And so how much we need to render of all the pixel in this area? We only need to render this much, not these pixels, because these pixels are again hidden by the pixels in front of it, right? We need to render only that much which is visible and which is not being hidden by the pixels in front of it. So that's the advantage we get if we are rendering front to back. If we are rendering front to back, we can avoid drawing the pixels which are hidden by pixels which are in front of them. Had it been from back to front, which is also known as the painter's algorithm, then Even though some pixel is hidden, still we would have to draw it, because I've been rendering it from back to front. I would need to draw all the pixels, and then there might be a bunch of fixed pixels which completely hide these pixels, right? But that I can't determine from beforehand, and hence I will be wasting computation while drawing these pixels, right? That's the problem. So that's the advantage we are getting for using front to back rendering. This is a very short intro into how Voxel Space engine works and how the terrain is generated on the screen. Keeping aside Voxel Space algorithm, we need one more thing which is very preliminary for the implementation of Voxel Space. How do we actually print or draw the pixels on screen? For this, we can use kind of any graphics library which allows us to get access to pixels on screen and which can render pixels for us on the screen. That's the minimum requirement for rendering Voxel Space. The other thing we might want to use is some sort of framework which gives us access to keyboard, so that we can use our keys to move around in our terrain. And yeah, that's it. So I thought of doing some other fancy stuff as well with my implementation of Voxel Space. One very common thing that used to be present in games implemented using Voxel Space would be fog in the terrain. It added effect into the game, as well as it also helped in hiding the clipping effect as we move forward along the z-axis and the terrain is generated at the farthest end of the z-axis. We sometimes get some sort of clipping effect, and fog does a very good work of hiding that. So I wanted to incorporate fog as well into my implementation of Voxel Space, right? So I started playing with fog. From the resources I followed, I came across two kinds of fog. So I referred to this article, right? And as you can see here, there are two kinds of fog majorly. One is linear fog and another is exponential fog, and we have got two different sets of formula to implement these two types of fogs, right? So right now the fog on screen uses exponential density, right? Let's see how it affects if we change the fog density, right? So you can see I can control the density of the fog using, and this is how it feels when I'm using exponential fog algorithm to change the density of the fog, right? It's pretty cool. And if we do the same for linear fog, this is the effect you get with linear fog. You can decide till what distance the fog should continue and where the fog should start. Right? Yeah, both the algorithms are pretty cool. I personally tend to prefer exponential fog, but yeah. And also I wanted to try out different terrain maps, basically color and height maps. So yeah, I added quite a few terrains. I found all of these online, like none of these are created by me, right? So yeah, there are pretty cool terrains as well. This is kind of red soil. I believe there is a snow as well. Yeah, this is a bit of snowy terrain. Yep. Cool. So yeah, so coming back to where what I was telling about rendering pixels. So I wanted a graphics library which could allow me to render pixel on the screen. And again, you can use any graphics library, but a few months back I came across this page, this awesome ossinsight.io, which kind of lists and ranks game engines by the number of stars they have gained or lost in across time, like the number of stars they have gained and lost. And if I say last 28 days record, like Raylib has always been towards the top. Like yeah, Godot is doing awesome, but yeah, we have got something called Raylib, and I was pretty curious into how, like, into this. It's super simple, and it's a super tiny game engine, and it's super simple game engine to use. And I was really curious about it, and I was interested to use it in one of my projects, and I thought, why not Voxel Space? So I decided to use Raylib. There was one tiny issue. I have never used Raylib before, and so I did this. I googled about Raylib. This is the homepage for Raylib, and as you can see, it's available on several platforms. You have got Windows, Linux, Mac, Raspberry, Android, and it has got lots and lots of language bindings, right? It's written in C. It has got bindings for C#, Golang, Lua, Python, and whatnot. I chose to go with C. Raylib also offers some extra libraries, right? It provides you Ray Math, Ray Audio, Ray GUI, Ray RPNG, and things like that. It also provides some. Also, there are some libraries, external libraries, which has been developed using Raylib, which are not only for game development but for other purposes. For example, like this one, Ray GUI, which allows you to create GUI components, like cool GUI components on screen, right? And in fact, this is the one which I've used over here for creating these bars, this toggle button. Yeah, Raylib is pretty cool. So when working with Raylib, your best friend will be this page. This is a page which you will find immensely helpful, because it lists all the Raylib API, and it has nicely structured it by core Raylib APIs, our shapes, our textures, text, and whatnot. Like, you can simply search your use case over here, and you can use the corresponding API for doing stuff with Raylib, right? Let's have a look at the code, the Voxel Space implementation. We have a common make file which works on both macOS as well as Linux. I have tested it on both Ubuntu and macOS. Right now I'm on macOS. You can have a look at this make file. I'll link to the entire code repository. I'll put it below this video. Let's head back to the main.c, which has the entire code for Voxel Space. And interestingly, if I look at the core part of Voxel Space, it's just this much. This is the core part of the algorithm where most of the work is happening, right? Both the rendering, both the drawing of the pixels, as well as casting the rays and going pixel by pixel along each rays. We start with declaring some constants using hashdefine, right? After that, one of the most important structs that we have is our camera struct, which will contain a number of parameters required for Voxel Space, right? We have the camera height, the camera angle, the speed with which the camera moves, the rotational speed with which the camera rotates, the speed with which the height of the camera changes, tilt, the z-far, and also all those kind of things. We create an initial, we initialize the a camera using this camera struct, right? We start with some suitable initial values, like we want our camera to be located at 512 and 512 initial position of the camera. We want to start off with a height of 150 for the camera. This is the angle. The other various initial values, like rotation speed is 0.5, etc. Here's the function for processing keyboard inputs. It's like pretty much what's mentioned in the Raylib cheat sheet. This one. So yeah, here I am using this function, right? This one over here. And similarly, like this, you can simply look up functions and their APIs, like the Raylib APIs, and you can use them directly in your code. Going forward, we have a function for generating the linear fork factor, the exponential fork factor, and finally, this is the function which scales our pixel, taking into account the fork factor. So this determines what will be the final pixel color like after we take the fog density into consideration. So this is the final scaled pixel we are going to render on the screen. This is a tiny utility function for loading our maps. Coming down to our main algorithm, as I mentioned earlier while explaining voxel, we need to divide this distance between plx comma ply and prx comma pry, the extreme 2 points of the extreme 2 ends of the field of view, by our screen width. So we divide it into screen width number of columns, right? And we cast that many rays. So here we loop screen width number of times, and then we need to find out what's the delta for every ray on the ith column. So the I is the column which we are processing at the moment. So for every column we need to find out what should be the delta x and delta y with which we should go along that ray, right? And we calculate this using rise over run formula for calculating this delta x and delta y, right? Once we have that, we loop along the zfar, like we execute this piece of code for every unit along zfar, and for every unit of zfar we find the pixel position along the ray we are casting, right? And that is what we are doing here. So rx comma ry is the position of a pixel on the casted ray, and using rx ry we find the map offset, right? It's a classic formula for converting a two-dimensional coordinate into a single offset in a buffer. The buffer I'm referring to here are basically two buffers, one which stores all the pixels linearly of the color map, and the other is that from the height map. Here we do some boundary checks and we make sure that things aren't going outside of our screen. Next we do our front to back rendering, right? We only render those pixels which are not hidden by the pixels in front of it. We only render that, right? And just before we are sure of the pixel we are going to render and the height, we scale it with the fog factor, and when we have the scaled pixel we draw it using Raylib API. So it's extremely simple. We just call draw pixel. We provided the x and the y position, right? And we draw it, right? It's as simple as that. These are some of the controls. Like this piece of code handles the GUI that is on the screen for fog density and maps, right? So I've used RayGUI. RayGUI comes as a single header file, which is pretty awesome. Like you don't have to link it with any library. It just comes with this raygui.h. You need to put it in your include folder, and you need to use it in your makefile, right? And you need to use this macro to tell Raylib that you are going to use RayGUI implementation. So it's as simple as that. So yeah, that's the implementation of Voxel Space using Raylib in C. To learn more about Voxel Space implementation, the algorithm, how it works, the history about it, like this is one of the best resources out there. This article by Codermind, it's pretty good. It might be slightly difficult to understand, but you'll get all the theory as well as I believe code examples as well in this article. Apart from this, the best video tutorial or video explanation I found of Voxel Space along with implementation using a different framework is this one by Pikuma. He has done a terrific job at explaining what's Voxel Space and how it works and how it's implemented. So this is a must watch video. The other one is this GitHub repo, which also provides a implementation of Voxel Space along with explanation, but in JavaScript. But this is also extremely good. It follows a different approach to rendering the pixels on screen. So as you can see, it follows a different process of rendering, or different approach to rendering. It's going back to front, right? It's doing the painter's algorithm. They have nicely explained rotation here and several other things. This is the front to back algorithm. And so yeah, this is one of the other best resources you will find out there for learning about Voxel Space, right? And actually you will find lots of resources here as well. The maps. So this is actually from where I've used picked up the maps for my implementation as well. You will find lots of color and height maps over here. This is pretty awesome. So yeah, that's it for this video. I hope you all liked and enjoyed this video. See you all next time.